Okay, one of my students gave me this stoichiometry question, so I just thought I'd do it online for everyone. So what we've got is a quantitative analysis of an organic compound showing that it contained carbon, hydrogen, and oxygen only. When 0.392 grams of this sample was burned in excess oxygen, it produced that many grams of water and that many mils of carbon dioxide gas at this temperature and pressure. Okay, so first of all, it's asking us to determine the empirical formula for this compound. So what I like to do to start with is I like to simply just write out the basic equations. To start with, we've got a compound with unknown amounts of carbon, hydrogen, and oxygen. So we'll just write that down. We've got carbon, which is unknown, hydrogen, which is also unknown, and oxygen, which is unknown. And we're going to burn that in excess oxygen to form carbon dioxide and water. So what I like to then do is then write down some of the things that they've given us. So we know that they're burning 0.392 grams of this. So write that down. We know we're going to get 0.32 grams of water. And we know we're getting 547 mils of carbon dioxide. Now it's important that we realize that because this is a volume of a gas, the temperature and the pressure are both important. So what I would then do is we're going to convert these to standard SI units. So the SI unit for volume is in litres, so this is actually going to be 0.547 litres. And the SI unit for temperature is Kelvin, so we have to add 273.1 to this. So it's just going to be 373.1 Kelvin. Cool. So, and kilopascals is the standard unit for pressure, so we're okay there. Now, what I'm going to do now is we know that the amount of carbons in our molecule will be determined by the amount of number of moles of carbon dioxide that is given off. And the same with the hydrogen. The hydrogen in the compound, when it's combusted, turns into water. So we're going to use the number of moles of both of these to find out what the relative moles of carbon and hydrogen are in the molecule. So let's start with that. What we're going to do is I'll start with carbon dioxide. So we know that the number of moles of carbon in the molecule has to equal the number of moles of CO2. And the reason for this is because the only place where the carbon dioxide can get the carbons that make it up is from this molecule. And you can see that one of these will make one carbon dioxide molecule. Now we're going to use the formula PV equals nRT, which we're going to rearrange for moles. So it's just going to be PV over RT. And that's equal to, well, the pressure is 101.3. The volume is a bit over half a litre. And we're going to divide that by the gas constant, which is 8.315, multiplied by the temperature, which is 373.1 Kelvin. Now, if we put all that into you're going to have to use a calculator for that. We put it all into our calculator, and we end up with, now it's always good to use scientific notation with these, otherwise you're just going to end up with lots and lots of zeros. So this is 1.79 times 10 to the negative 2, and I'm going to write moles. Cool. So what we're going to do now is we're going to work out the number of moles of, we're going to work out the number of moles of water, and then as a result work out the number of moles of hydrogen. So we know that the number of moles of hydrogen in the molecule is going to equal 2 times the number of moles of water produced. Now the reason for that is because one hydrogen goes into making, you need two hydrogens go into making one water molecule. So if we have one water molecule, to 1 mole of water to finish up with, we know we would have needed 2 moles of hydrogen to make it. So the way we're going to work out what the number of moles of water is we're just going to go is equal to the mass divided by the molecular mass, which is just equal to 0.32 over, I think water is 18.016. Yep. And then once that's going to give us our number of moles of water, and then we're going to have to multiply that by 2 to get the number of moles of hydrogen. And we find that that gives us 3.55 times 10 to the negative 2. Sorry, I just had a bit of a problem with the calculator then. Okay, so now we've figured out the number of moles of hydrogen, the number of moles of carbon. The only way we can figure out the number of moles of oxygen in this molecule is if we just work out the mass of oxygen left over. So what we're going to do is we're going to work out what the mass of 1.79 times 10 to the negative 2 moles of carbon is, and what the mass of 3.55 times 10 to the negative 2 moles of hydrogen is. So we'll just see if we can squeeze it in down here. The mass of carbon is going to equal 12.01 times 1.79 times 10 to the negative 2, and that's equal to 0.215. grams. And the mass of hydrogen, we're going to do exactly the same. We're going to get the molecular weight of hydrogen, 1.008. We're going to multiply it by the number of moles we have, 3 times 10 to the negative 2, and that gives us 3.58 times 10 to the negative 2. Great. So what we're going to work out now is we have to figure out the mass of oxygen. So the mass of oxygen will come over here. Let me just... So the mass of oxygen is going to equal the mass of the sample, which is 0.392, subtract the mass of the carbon and the hydrogen added together, which is equal to, well, the carbon is 0.215 grams, and the hydrogen is 0.0358 grams. We find that is equal to 0.141 grams. Cool. So we can then work out the number of moles of oxygen pretty easily by going the mass of oxygen divided by the molar mass of oxygen, and that equals 8.84 times 10 to the negative 3 moles. Okie dokie. So what we then do is we're going to line up our 3 compounds. So we'll put this in a different color, make it easier to see, and we'll separate it a bit. So we'll get the red. So we have the carbon, we have the hydrogen, we have the oxygen. Cool. So, and the number of moles of carbon is 0.0179. The number of moles of hydrogen is 0.0355, and the number of moles of oxygen is 0.00884. Now, hopefully you guys are aware that to get the empirical formula, we're just looking for the ratios of each of these, the molar ratios of each of these elements. So what we do is we divide each of them by the smallest number. So this one, it's going to be the oxygen amount. So 0.00884. And obviously that's going to equal 1. So we divide hydrogen by 0.00884 and we get 4.02. Then again, carbon 0.00884, and that gives us 2.02. Okay, now these are never usually going to be exactly right, but as you can see with these ones, that's basically 2, that's basically 4, and that's 1. So from this we can then write, therefore the empirical formula is equal to C2H4O. Okay, so that was A. Now lucky that's one of the more complicated ones. So what we're going to do is I'm just going to separate all this. And we're going to do B. We'll get rid of this. And we'll do B up here. So I'll just... that line sucks. Just don't worry about the line. Okay, so B, it says determine the molecular formula for the compound. Okay, to work out the molecular formula for the compound, what we're going to do is we're going to use this second or third paragraph here and the PV equals nRT equation. So we've got B up here. So we're going to use this number of moles is equal to okay. So we just literally substitute in all of these values. So we know the pressure is 194 kilopascals. The volume is 100 mils, so that's 0.1 litres. We know the gas constant is 8.315. And we know the temperature is 250 plus 273.1. So, and that equals 523.1. And we find that that is equal to 4.46 times 10 to the negative 3 moles. Okay, so what we then can say is that therefore 0.392 grams is that many moles. So we can then go, well, 1 mole will equal to 0.392 divided by 4.46 times 10 to the negative 3. And that's equal to 87.9 grams per mole. So that's our molecular weight. And what we can also, then what we're going to do is we're going to say what our molecular weight of the empirical formula is. So we're going to go so 2 times 12.01 plus 4 times 1.008 plus 16 ends up being 44. So what we can then say is, well, 44 is exactly half of the molecular weight of the actual molecule that we've got. So therefore, the molecular formula is going to equal 2 times the empirical formula, which is equal to C4, you idiot, H8O2. Cool. Now, what we know, so we have straight on to C. Sorry, I was just reading what we had to do for C to myself. So for C, it says the compound was reacted with methanol and was found to produce a liquid that smelled like apples. Okay. So if it reacts with an alcohol to produce a nice sweet smelling liquid, that sweet smelling liquid is going to be a ketone. So yeah, and so the thing that reacts with an alcohol to produce a ketone is a carboxylic acid. So it has a carboxylic acid functional group on the end. So if we just write that in red here, you can see that that's what we're going to have sitting on the end of our molecule. Now, for C1, we have to draw a structural formula for the compound. Now, this has to be on a terminating end to produce a ketone. Now, it's not a ketone, it's an ester, sorry. So, what we're going to do is we're going to have our carbon chain. So there's going to be 4 carbons. Now, we're going to have 1, 2, 3, 4, 5, 6, 7 hydrogens. 3, 4, 5, 6, 7. And on the final carbon, we're going to have both of our oxygens in a carboxylic acid functional group and our last hydrogen. So that is going to be the structural formula of the compound that's produced. Now it says name the product formed when it reacts with methanol. Okay. So what we have here is meth, eth, prob, but. So it's this one here is a butane or butanoic acid, if you like. So when we're writing an ester, we use the start of the alcohol. So it's going to be methyl. And then we write the butane group on the end. Butanoate. Now these are things that you're just going to have to memorize, but the rest of this is, I find, just almost common sense. But the main parts are you've got to write down the equation, find out the number of moles of all the things that you can. If there are any elements left over, you're going to have to take them away from the mass of the sample. You then use each of the moles to create a ratio, and with that ratio, you're going to work out the empirical formula. You're going to use, to find a molecular formula, you need to find the molecular weight of the compound by whatever means necessary. You then figure out how many times bigger or smaller, it can't be smaller, how many times bigger the molecular weight is from the molecular weight of your empirical formula. And then to get the molecular formula, that you then just multiply it by that factor. In our case here, it was 2. Now, for C is just you're going to have to rote learn these. And I'm sorry about the misunderstanding with the ester. Just had a bit of a brain fade there. Okay, well, I hope that helped. See you next time.